And a headphone.
Okay, I think I'm in. Hello.
There you go.
How's it going, man?
Welcome. Sorry about that. I'm a complete noob when it comes to Discord.
No problem at all. Good to have you here, Robert.
Thank you. So, wondering if you had anything you want to pick the brains of a physicist.
Yeah, real quick, before you start, can you tell us what you're a physicist of and maybe a little bit background so we can kind of know a little bit about you, if you don't mind?
I am a cosmologist at a university in Britain. I'll prefer to just leave that unnamed if that's okay with you.
Yep.
But I'm a cosmologist, essentially. I work with the early universe.
Oh,
cool, man.
Sorry.
So you study celestial objects? Is that what it is?
No, that's way too new for me. I study background radiation and what happened, during the original Big Bang stuff, inflation, all that kind of stuff. When stars and stuff have formed, it's already way too recent for me. I mean, I know the stuff, but my research is before stars form.
Okay, like the microwave background radiation and stuff like that.
Much before galaxies form.
Okay.
Before. I mean, we kind of look at the superstructure of galaxies because it tells us something about how the universe began. But I don't actually look too much at the individual stars.
Are you in touch with the people in Antarctica doing their research down there about the microwave background radiation and that sort of thing, or is that something different to what you're talking?
I don't have anything to do with that research. I'm working with ESA vaguely. With there's a probe that's going to be launched in 2024, which is going to be measuring some background radiation. I'm doing a little bit of work with that, but that's about it.
So Robert, do you know? Have you ever looked into flat Earth?
Oh yeah. I've been talking to flat earthers for 2 or 3 years or so. It's I enjoy it.
That's cool, man.
So Robert, you understand the background of the initial flat Earth claim, we see too far. The spherical geometry does not adhere with the reality of which we measure and observe. You understand that, yeah?
I've heard all those claims before, yes.
What gives you the stance that you do right now at this point, studying the cosmology, that some people come in here and say that there's terrestrial planets out there? What give you the idea that there is that, information that you can go ahead or evidence that you could cite, maybe?
Sure. I mean, again, that's not the stuff that I do, but I mean, I know the science that's going on. It's kind of cool because it's pretty new. It took us. It's only like 30 years ago we detected a planet around another star. Before that, we had no clue that there were any planets outside our own solar system. But we found them. We have really cool ways of finding them. I don't know how much detail you want me to go into with that. I can explain how we see them, how we know they're there, and how we know what they're made of, all that kind of stuff. It depends how curious you are, really.
Could we get what they're made of from you? I mean, can you explain that?
The way we do that is because we have a really fortunate thing called spectral analysis. It turns out, if you go into a lab, forget all about planets and everything outside in space for now. You just go into a lab and you take all the elements that we know. We've detected elements for hundreds of years. We have a whole periodic table. We have them all in the lab, right? And what we do is we put this, we send electricity. We really force a few electrons through this gas, because what happens is that the gas sends out light. It starts emitting light when we shove electricity through this gas. This is well known. This is how light bulbs, modern light bulbs work. That's not a big deal. The great thing is, though, that the lights that it put out is dependent completely on the element that we're looking at. There are some, and that's called the spectrum of the element. So every single element in the periodic table has a completely different signature of light to it.
Like a fingerprint?
Yeah, completely different. There are no two elements that have the same spectrum. So that means it gives us an incredibly cool way of knowing what element we're looking at simply by looking at the light from this element, because the light from the element is the indicative of what the element is. That's really practical when we're looking at stars, because one thing that stars do, obviously, is send out light.
A quick question.
So if we analyze the wavelengths of this light, it tells us exactly what the stars are made of.
Can I ask a quick question?
astronomers and physicists in general.
Can I ask a question?
So that's how it's used, and we can look at the starlight,
Let
which
him
is
finish
reflected.
explaining.
Being muted or something?
Ask a quick question, please.
No, Robert. Chad is asking if he can ask you a question.
Oh, go ahead.
When you say you can tell what things are made of by the light they emit, is it the thing that you're telling what it's made of, or is it the atmosphere of the
Can you hear
thing
me?
round it? The atmosphere. Can you hear me?
I can hear you, Chad.
You can't hear me. Robert
Can
can't
you
hear
hear
me.
us, Robert?
Me?
Robert.
Hello. Can you hear me?
Robert.
Yeah, we can hear you, Robert. Can you hear us?
Okay. Yes, I can hear you perfectly.
Okay, so Chad's asking you a question right now, so go ahead, Chad.
Can you hear Chad? Sometimes
No.
there's a thing where you won't be able to hear certain users. I don't know what
can't
that
hear
is.
I didn't hear a question from anyone.
Oh.
Question. Can you hear me now?
Can you repeat the question, maybe? The people who I can hear?
I am
That would be
I'm repeating it
fine.
now. Is it the object that you're seeing the light from, or is it the atmosphere around the object which you're seeing the light from?
I'm hearing nothing. I'm sorry.
Oh, hey, Robert, will you just try leaving the voice chat and coming back, and sometimes it resets the sound?
Press back, I guess. Just hold on.
Just like disconnect and then reconnect.
I'll try.
Yeah.
That's
A
a
little
problem.
phone button.
It's a problem with
Yeah.
Discord.
It's the phone with
Refresh on the
wait, it's-
page. That's what I do. Hear me now?
Okay, yes, I can hear now. Are you Chad?
I'm Chad. Yeah, I was asking.
Yeah,
Is it the
perfectly.
object which is that is emitting the light that we can see, or is it the atmosphere around the object which is making the color of the light different?
If we're talking about a planet, an exoplanet, is that what we're talking about?
Anything we see in the sky, is it? Are we seeing what the actual planet's made of, or are we seeing what the atmosphere is?
We would be seeing the atmosphere of exoplanets. That is what we're able to see.
Right, so we don't actually know what the planet looks like itself then.
We have a very, very bad low resolution image of something called the Beta Pictoris system, where we can see a few pixels of the planets, but that's all we have. We don't have
Actually
any
seeing
clear
the planets, we're seeing the air around the planets then, yeah?
Well, I mean, of course you're going to see the surface of the planet. I mean, you can't look through a planet. It's opaque. So yeah. We are definitely not in the position to see actual, good images of planets at this point at all. They're way too far away.
You talk about the planets in our solar system, Robert, or what planets?
Sorry, no. We're talking about exoplanets. We're talking about planets around other stars. We have very good images of our own planets. But
okay,
if we're looking
I just didn't know. I wanted to be clear about what you were saying.
Yeah, sure. We have excellent imagery of our own solar system, but we don't have pictures of other planets around other stars, aside from a few pixels, which were basically just there to show that we could do it. It's really, really hard to see them because the star, of course, is very bright and it's blinding out the planets. But we did manage to do it once.
Hey, Robert. Can you hear me?
Yes.
Am I in the channel? Yeah.
I can hear you. Yeah, sure. Hello.
Wait, you can hear me?
He can hear you.
He can.
Yes,
I can hear you.
Have you heard about
Maybe you can't hear me.
sonoluminescence?
Sonoluminescence is this weird phenomenon which causes light from sound waves and bubbles.
Yeah, in water. So what? Scripture has the word of God. It has the dividing of the waters, and it has the light. I mean, that's all of the constituents of that scenario right there. So,
I mean, if you want to interpret that Genesis line as sonoluminescence,
No, we're not talking about religion here. We're talking about the flat Earth.
No, but I mean, it's fine. If you want to interpret it like that, I'm not going to.
No, it isn't fine.
In that case, I won't answer it then. Anyway, Chad, did I answer your question as you wanted? Because I feel like we didn't get into the atmosphere versus surface.
I mean, like the sun.
Discussion.
You know, are we seeing what the sun's made of, or are we seeing the sun's atmosphere?
We are mainly seeing the atmosphere of the sun. I will
We
agree.
don't know what the sun's made of. Then we're just seeing the atmosphere.
Well, we can see what the atmosphere is made of, but the thing with the sun.
Do you know
is
what
that
the
it's a
sun's made of, or not?
Oh, the atmosphere of the sun is
What
made
the
of, and
atmosphere
we
is
have
made of.
Yes, and we have very good seismic data for deeper into the sun, and of course we have clear understanding of what's going on in the core of the sun.
Sorry, did you say seismic data?
You can only see the atmosphere of the sun. That's all you can see, isn't it?
Well, yes, but
because of spectroscopy. I can't even speak. Spectroscopy. I just had a coffee. I can't speak. Sorry.
Spectroscopy.
But I think what you need to remember is that the light that comes.
We're talking about what we can see.
Can I
see,
respond?
when we look at the star, what we see is its atmosphere, isn't it? Not what the actual star is made of. Wrong or right?
You're completely right. What we see directly is the atmosphere of the sun.
So we don't know what the sun's made of, do we?
Well, we do, because the sun is not.
The sun is not spectroscopy.
Or
let him speak.
The thing about the sun is it's not a solid object. The photons that come off the atmosphere come from inside the core originally. That is how the sun works. It is a ball of plasma.
Okay, I have a question, Robert. How do you know that?
Well, because we can see the motion. It's not really.
I'm saying, how do you know it's coming from the core of the sun?
Yeah, that's a good question. We know that because we can see the convection patterns. Do you know what convection is?
Yeah, we know what convection is.
Convection, you can see the way the flow of the plasma is working. That we can see, and we can see the magnetic fields of the sun. At least we can measure it. And the magnetic fields also tell us how the plasma is moving.
Okay, but you were saying that you can only see from the atmosphere of the sun. But you said
we can only see the surface.
How do we actually measure the magnetic field of the sun?
It's kind of difficult from the Earth. That is a good question. It's really hard to do from the Earth. We have a solar probe which did it. You have to actually send the probe.
That's what. I know we can measure magnetic flux with a Gauss meter or a flux meter. So I was wondering who probed the sun or got close enough to get a Gauss reading or magnetic flux density reading of the sun.
Exactly. We had a probe of that. I can't remember what the probe's name was. It's about 10 years ago. We did a really nice mapping of the solar power, and it has some really weird properties, which we have no idea why they do. I mean, it has a northern magnetic pole, but not a solid southern one, which is super strange. But whatever.
How close did that probe get? Do you have any idea?
I don't know. Closer than Mercury, definitely. It was
incredibly. It did not melt. Yeah, I was about to say, what kind of material? Because I like material science myself.
That's cool.
What kind of materials?
Is it the Parker one? The Parker solar probe?
Parker's
probably. Honestly, I only know about this probably from.
Just summarise what I think of what you've said, Robert. Before I'm going to stop talking after this. Basically, you said we can know what the sun's made of because of this spectroscopy. We can only see the atmosphere. We don't know what it is. So you just lied, and I'm finished with you. Thank you very much.
That's cool. Anyway, anybody else?
It's also fallacious reason.
Hey, Robert, if you look in voice text for everyone, I have a little shot where it's a picture from ESA where they show an event on the surface of the sun where it causes ripples in the sun's surface. Cool. So I want to know how that could happen if the sun is not, or is a gas, or is just plasma.
I mean, there's no big. You think that these ripples would require a liquid? Is that what you're implying?
Well, does that happen in plasma? Because I've never seen it happen in plasma.
It happens in gravitationally bound plasma, of course. All you have there is an emission of energy. I mean, I've never seen this photo before, so all I'm just doing is looking at it. But these ring waves, that's a disturbance in gravitationally bound plasma. It doesn't surprise me that it looks like that. It looks cool, though. What's the scale?
How do you know that it's gravitationally bound plasma?
We know it's plasma. because we can measure the temperature of it and we can measure the composition of it, and that's just we know the pressure, we know the temperature. It's not a big deal.
You're measuring the composition, okay, from the light based on you're inferring it or correlating it to the composition of metals or the light that's emitted by the plasma of the metals here on Earth, correct?
Not metals, because
well, like sodium metal, or you can go noble gases. I mean, metals do. Like I play around with this stuff too. Believe it or not, I like vacuum stuff, especially lighting stuff. So yeah, I mean, mercury is a metal, and we have mercury plasma or mercury vapor lamps. Sodium is a metal, and we got low pressure sodium and high pressure sodium lamps. And yes, we do know that, like the spectral, whatever. What do you want to call it? The spectroscopy of it, or whatever, that complicated word. So you're just correlating that data with whatever you're getting from the sun, right? And then you're hypothesizing that, hey, you know what? Since this is like that, thus the sun is X metal, or a blend or amalgam of these metals, right?
Well, apart from the fact that it's not metals, it's hydrogen and helium. But yeah. We have no other way. Yeah, but that's beside the point. We have no other way of getting those spectral lines unless hydrogen and helium are present, basically. Those spectral lines will only occur if hydrogen and helium are there. So we know what the sun is made of from the Fraunhofer spectrum. Does
it emit sodium spectral lines or not?
Yeah, it has some sodium in there, but it's not very clear. But it does have some.
It does, right? Doesn't it?
You say that it was the atmosphere which makes the light. And you've just gone back again. We've already told you it's the atmosphere. You just said it was, and you've gone straight back to saying it's the sun.
The atmosphere is part of the sun.
We're analyzing the light from the sun, correct, Robert?
The light that is emitted from the surface of the sun. That's all we can do.
Oh, correct. Right. From the sun. I just call it the sun. I do not know what it is. I'm just analyzing this light that I'm receiving here on Earth, right?
Yep.
It's not science then, is it?
It's definitely not science, is it, Robert?
Yeah.
It's good correlation, but it's not definitive.
Yeah, it's not. We're not doing science here, are we? We're not proving cause and effect relationships, are we? It's just correlations and inference.
You wish to call it that, but I would just like to say, what on earth? What else would make those spectral lines if it's not those?
So you do agree that it is an assumption then? But like, as you might put it, an educated
guys. You got to stop being hypocrites and stop yelling at him. You're telling.
No one's yelled. Angry. No one has yelled.
You're putting him down like what he's saying is like is just ridiculous. It's like you sound like a bunch of children, not even considering.
Shut up.
Yeah, mute that guy.
Sorry, I can't deal with that. No one's shouted at you, mate. So let's carry on.
No, I'm fine. I'm completely fine. Yeah, I mean, I get what you're saying. You're saying that it is not definitive proof.
Right. So we would say it's an assumption, though, right? Wouldn't you agree? An educated guess?
I would say that it's much closer to being a fact than being a guess.
Okay, but you're still dancing. I'm a flat earther, okay? And you came in here and called yourself a physicist. So be honest to me. You don't know what the Polaris star is made up of, do you? You don't know, do you?
I don't know, because that's not how science works. Science works by getting the best possible guess.
No. You're a physicist. You're a scientist. You do know the scientific method, don't you? So science proves cause and effect relationships, doesn't it? Don't start telling me this isn't what science does. Science proves cause and effect relationships, yes?
Science proves nothing. Science establishes theorems. Proofs is for mathematics.
Pardon?
Oh.
No, hold on. Let me get this right. Let me get this right. Scientific method, we are doing cause and effect relationships. Science studies the physical and natural world. The question we ask is, what causes that effect? After we have proven cause and effect relationships, after experiment and validation, we can then move on to scientific theory, taking the things of which we have proven and building our theory upon the things that we have proven.
And nope.
I can't believe I'm actually explaining this to a physicist.
We need to agree on what proof means before we continue this. Because I would disagree on that definition, essentially. What a proof is. Because you can't prove anything in natural sciences at all. All you can do is get very close by consistently attempting to falsify your theory. And if it fails, then you get closer to the truth.
You're talking about logical. You're talking about logical deduction, Robert, right? Logical deduction.
I'm talking about proof, as in what happens in mathematics and logic. Yes, and that doesn't happen in science.
Hold on. Do you think maths proves things?
Of course, maths proves things, but it doesn't prove anything about the natural world.
Okay, so maths not proving things, yet we're studying the physical and natural world, and in science we prove cause and effect relationships. After we've proven those causes, we can then go on to build scientific theories.
Is your definition?
So no, your maths isn't proving anything, and you're not doing any actual science, are you? You're basing it upon an assumption.
Try again.
And it's not his definition. I have 5 university papers that actually comply with what he's saying, if you'd like to see them.
What I'm saying is, mathematically, you can prove things within the realm of mathematics. There you have proof. It's easy. You can prove lots of things.
Can you put yourself on mute? I can hear you.
Hear me?
Your hot mic and Vito.
What's good, gamers?
Am I visible?
What's good, gamers?
Can you hear me? I think maybe
we can hear you. Yes, we can hear you.
Oh,
How
okay.
are you doing? What brings you to this Discord?
Hold on, G1. We're having a conversation, bud.
Heck yeah, hold on.
Proof.
No, we're talking to Robert. Hold on, man. Continue.
So it's about what proof is. I mean, is it the big question is, can you prove any statement about the natural world?
If you can physically manipulate your presumed cause of the effect, then you've proven the cause of the effect. It's not like you are going to the sun or the stars and physically manipulating that actual thing. You're basing it on the inferences of things that you can do here, and the formal logical fallacy because of what you say light in the sky does based on your inferences. This is not science. You're not proving cause. You can't physically manipulate the sun, can you? You can't get there.
What you're saying is indirect measurement doesn't count for you. Is that correct?
Indirect measurement. Well, it's a nice inference, as I said, but you're not doing science. That's the only thing that I'm saying.
So look, you have 2 methods. You can do non-experimental, where you lack independent variables. And the best you can do with non-experimental is correlate. And we know in science, correlation is not causation. Now, if you want to establish a cause for something and prove that's what it is, you then do you have to manipulate that independent variable so you can establish that cause and effect. So a non-experimental, you lack the independent variables. Experimental, you have a manipulation of it.
If you want to establish a correlation, you cannot prove a correlation. Not in science. It's just not possible. But you can get really, really close to accepting it as true. That's easy. But I think we need to talk about what an indirect measurement, why would that be a less plausible measurement than a direct measurement? Would be the problem.
Can I say something about the sun and the spectral lines real quick, Robert?
Sure.
Let's say if I have a source, because that stuff, it's very intriguing. Let's say if I have a source of some ultraviolet electromagnetic radiation, correct? And it's contained within a boundary. On this boundary, I have phosphorus, which we know it does react with ultraviolet electromagnetic radiation and emits light. Now we can change the composition of the phosphorus to get whatever, light temperature we want. Now, if you, with your measuring device, with your whatever, however you're going to do your spectroscopy, or whatever that word is, what kind of spectral lines are you going to get? And are you going to be able to tell that this is coming from a UV source inside of this boundary? Or are you just going to pick up the light from the phosphorus?
It will just pick up the light from the phosphorus.
Correct. So you'd have no clue what's going on inside of the phosphorus bulb, right? These are whatchamacallit, what do you call it? These are the UV bulbs. I forgot.
I see what you're saying. But
I'm saying? Back to the sun, because you were saying we're just picking up these spectral lines from the sun. So you said it's fact, like we know what this is, right? But we've got no idea what the primary mechanism could be. We've got no clue. Like you'd just be picking up the stuff from the phosphorus, and you've got no idea what's going on inside, or if there is an insight.
I will disagree that I have no idea. Of
Well,
the composition
okay.
of what's inside the lamp, but I do know how much energy is coming out of it.
I think he's saying to be certain, not have an idea, because that would just leave you open to saying that, yeah, I could have an assumption, but not to be certain about it. And I think that's what he's getting at.
I think what I mean, correct me if I'm wrong, but I think the question was, if you can only see the surface light of this phosphorus, then you can't know anything about what photons stimulated the phosphorus, right? That's what he said, and I agree with him. You can't necessarily say anything about that, right? So it's not just an assumption, it's just about that. But we do have information about what's going on inside. Not necessarily.
Well, because I brought you an example of the fluorescent bulb, and we know how that works. And we know that phosphorus reacts with UV. So again, back to the surface of the sun and what is the primary, the prime mover for this light? We have got no clue. We're just analyzing the light, and then you're deducing, or you're correlating. Oh, okay. Let's say the sun is emitting a very high spectral line of sodium, thus it's sodium. It has a sodium core. You can't do that, really. You can assume, sure, it's just an assumption, though, and that's it. It's not fact. And you can't write it in a textbook as like, oh, yeah, we know exactly what's going on.
I see what you're saying.
Again, with the fluorescent bulb, you're just picking up whatever light the phosphorus blend I put on the outer shell of the bulb is. And, of course, if I make the bulb out of quartz glass, it's going to let this UV come through, and you will be picking up UV, too.
So, okay, let's say that we're an alien, and we found this fluorescent bulb, right? And we have no idea how it works. We have no clue how it works. And we do spectral analysis on it. And we see, okay, we're getting some lines from it. And by analyzing those lines, there's phosphorus. Do you agree that's definitely that's the conclusion we can make, right? And that's not an incorrect conclusion.
No, it's not incorrect. No, it's not bad.
So what we can say is then they can say, okay, well, what's going on inside this? We can also measure how much energy we are getting out of the light bulb, right?
Sure.
So we can say something about, well, how much energy in total are we getting out of the light bulb? Meaning we can calculate energies are going into the phosphorus to excite it, to make it transmit this.
Within a margin of error, of course, because there are losses, as you know, for sure, of course. But yes, I'm with you.
That means that we have information, indirect information, about which energies have excited the phosphorus.
But then you have to know how phosphorus works, though. And you said we've got no clue. We just picked up phosphorus spectral lines.
I didn't say that. I said we're aliens who found the phosphorus bulb. We're assuming that these are aliens who have actually done experiments.
Yeah, but that's a hypothetical, Robert. We're getting into the realm of like hypotheticals, and we're trying to get to the basis of understanding things with certainty, and we're going into like aliens, and that we're getting off the topic, even talking about what we're subject here. So yeah, I just want to bring it back to that. But no, we're going to ask a few more questions, but then we're going to try to get to the shape of the Earth and so on. So, but please go ahead and finish what you're.
Okay, cool. I mean, the only reason I mentioned aliens was just to sort of get this concept, because what you said was that we already know how a phosphorus bulb works, so that's why we know where there's UV. So I just added the aliens to give an sort of a framework where we could talk about it. I'm not actually saying that there are actually aliens looking at the light bulb. Yeah.
Right, I get
is though that if we understand how emission works and how emission and absorption lines work, we can calculate by the energy output what the energies that were used to excite the phosphorus were, and then we can correlate that with other spectral lines because those energies would be UV energies, and we'll be able to say, okay, well, it's definitely not argon inside because argon cannot emit this energy, etc. So we can infer it like that. It's not these poor aliens or whatever who are looking at this light bulb are able to
Mercury. You brought up argon, noble gas. Mercury does emit UV, though. So would you know that it's mercury, or would you know that it's just UV?
No, you'll know which wavelength. That's the whole point.
Well, you can't. It's blocked by the glass. You're only picking up the phosphorus. You're not picking up any UV.
No, because you know that
the boundary conditions do not allow this higher excitement of electromagnetic radiation to pop through. So you're only getting the secondary excitement.
Matter if we can see that the phosphorus has been excited to, let's say, the third energy level or whatever. If we say that's happened, then we know what the exact energy required to excite it to the third energy level is, because we know phosphorus. Energy, we know what the exact energy of that photon was, and then we know which elements have emitted that photon inside the bulb. It's not just UV or not UV. It is a direct measurement. there's a clear number that we get, not just...
We have a direct measurement of the emitted light, correct? But we kind of, if we don't break the bulb open, we have to assume from here on out, correct?
No, nope. That's the whole point. If you
no,
can,
you can't. You can never ever know that there's mercury inside of the bulb because you're not going to pick up any spectral lines related to mercury if I design the glass composition correctly. And I do play around with this stuff. That's why I'm just bringing it up because of the sun and all of that. So I do have some plasma chambers and stuff. I do play with this stuff. So I'm sorry if I just caught you off guard, but it's all good. It's very interesting to me, like, you know, how you guys figure this stuff out without actually probing the sun. It's extremely interesting.
You can totally tell that you understand this stuff. But what I'm saying is, since you understand this stuff, right? So you know that if you get the full spectrum of visible light from Mercury, you get the full spectrum of all radiation from phosphorus on the sort of the outer bound of this light, right? If you know that, then you also know the energies that are being emitted from inside.
Well, I don't know how much losses are going through, but sure, we can, you know, I can say in order for me to get this much light, I would need this much excitement. Okay, fine.
Because to excite phosphorus, you need the exact right wavelength. Otherwise, it doesn't get excited. Then it just passes through.
Okay, cool.
So if it's been excited,
I do know the properties of phosphorus, correct? So this element that's going to react with my primary waves, you know, that's going to give me secondary waves, you want to call it that. I know some properties about the phosphorus, but if you correlate that with the sun, okay, the sun is emitting this stuff, and I've got no clue what the surface of the sun is. Now you can say we got these hydrogen fusion reactions in the flares of the surface, right? But that's also an assumption. We don't actually know. Like phosphorus, we can probe it because we know about it. We have it here on Earth. We don't have a sample of the sun. We never sampled the sun.
Let me understand what you're saying. You tell me that
we've got no idea what the primary mover or the secondary mover is, or, you know, the secondary, you know, stuff that's emitting the visible light. And we've got no clue if there's a primary electromagnetic radiation that's causing the secondary electromagnetic radiation, which is visible in spectrum.
Okay, so what you're saying is, let me just understand what you're saying. You're saying that it's possible for us to detect the phosphorus in the light bulb by looking at the lines coming out of the light bulb. Time that it's not possible to say what the surface of the sun is made of, but that's the same method. So why does one?
You can infer that, yeah. If let's say you pick up phosphorus spectral lines, yeah, you can, you know, make an assumption, a good scientific, you know, assumption that, yeah, okay, so the surface must contain phosphorus, right? That's fine. I'm okay with that.
So what's the problem with applying the exact same method to the surface of the sun?
Well, the phosphorus, I brought up the phosphorus to be specific because phosphorus works on, you know, it's a secondary thing. There's a primary, which is the UV. You know, primary emittance, you know, then it's exciting the phosphorus, then it's giving you the secondary light. So with the sun, you're just analyzing the visible, and we're drawing conclusions with the visible stuff, but we really have no clue what's going on. Anyways, I'm sorry if it's taking too long.
Jump in a sec.
You guys can switch subjects or whatever.
Fine, but
I like
it's a cool thing to discuss. So
no, it's very cool. I kind of like this stuff.
We are able to know what the surface of the sun is made of by the exact same method that you use to detect the phosphorus.
Yeah. Right, yeah. You assume that it's phosphorus, right? Unless you actually break the bulb open and you sample what's inside, right?
Well, no. I think there's no other reason for those phosphorus lines to be there.
Because we have phosphorus to begin with, and we have measured what phosphorus emits, and we recorded that. Thus, we know, okay, phosphorus, because we actually played with phosphorus to begin with, correct? That's how we know these. Agree? Okay, then, all right. So, because we have had this stuff in our hands, and we played with it, measured it, recorded it, okay, phosphorus emits X, you know, quantity X. Thus, if I measure some light and it gives me quantity X, then most likely it shall be phosphorus. Cool. But now, give me a piece of the surface of the sun, So I could play with at home and measure that, and then I could tell you, same way we did with phosphorus, because you played with phosphorus to begin with. But if I give you this new, if I come out with a new substance that is not phosphorus, this crazy amalgam, maybe it's just a mixture of all the stuff, who knows? Just this new element, let's say, right, hypothetically, right? Let's say new element you never played with, and it emits crazy spectral lines, all of it. Would you know what this element is?
Do you know what? This is actually kind of cool. Can I tell a story about this? Because you are actually putting a finger on something which has happened in reality with the sun.
Go for it.
When we started doing this spectral line stuff, that happened in the early 1900s. That's when we figured out how all the spectral lines worked. And everybody, of course, we took whatever element we had on Earth and we measured the spectral lines. That's what you're saying. Like, we got them, we have them in our hands. We have hydrogen in our hands. We have lithium. We have everything. We can test all this stuff and get all the spectral lines. And that's what we did, of course, because we're physicists and we're massive geeks. So we do this immediately, and we have all the spectral lines, and we're really happy. And then we look up into the sun and we see these absorption lines, and we say, hey, check that out. That's how cool is this? The lines for hydrogen is in the absorption lines of the sun. That must mean there's hydrogen in the sun. That is the conclusion, right? And we do this, and we find lots of lines. And you know what? When we figured out all the lines that we knew, there were some spectral lines that we didn't recognize. We were exactly where you told me, where you said, what happened? There's an element we had never seen.
Right on. Right on. That's the point I was getting at,
We noticed this in the sun. We're just like, what the hell is this element? We have never seen this in the lab before. All we can say is, okay, the lines are here, but we've never noticed it before. So we named the element after the sun. We called it helium because we'd never seen this element before. Helios, of course, heliocentric. Right. This is the word that every flat earther knows. We called it helium because we noticed it in the sun's lines first. What this is.
Right on.
And then later, like 20 years later, we finally isolated helium in the lab, and we're like, oh, we found it. That's what it was. Sun first. That's why it's called helium.
No, I get you. I like helium. Gives you a nice reddish glow. Pretty cool.
Cool substance. It's an absolutely insane substance. It escapes into space and stuff. Cool. Anyway, I feel like we talked a lot about this, and there were questions about the shape of the Earth, I guess you want to get to.
Yeah, we got light nerdy on these guys. I'm sorry, guys.
Yeah, we got people probably waiting in the wings. Does anybody want to ask?
No, it was fun. I enjoyed listening to that. I think we understand what is and what is not going on here.
We gotta be careful when we're like pretending to be logical, because, well, I know that's a bit of a vague statement, but Platonic logic is kind of hard to stick by because it's the razor's edge, So.
Right. Is there any questions that anybody has? Since Robert's a physicist and people want to ask questions and
So
find
Robert,
out.
Could I give you, say, a metaphysical question? You just like what you think about it.
If you want to give it to me, I mean, I'll just answer on that level that I can.
Okay.
Sure.
So, do you think condition is unconditional?
Can you define your term, please?
Condition being being or definition.
Are you asking me if you think that existence is necessary, like logically necessary?
No, not necessary. No, not like that. Like, it's kind of like this. When something is conditional, it's a factor. It's part of a multiplicity of sins, right?
You sure?
Right. So
yeah, go ahead.
Multiplicity is kind of the derivative here, because everything derives from it, from self. What would be the word? Oh, I don't know.
Kind of struggling understanding what you're saying, but is this kind of the question of why is there something rather than nothing? Is that kind of what you're asking me?
Yeah. I guess if you can treat it like an open-ended question, then go for it.
Okay, well, that's a great question. I don't know. There is something, and I really can't tell you what nothing would be like. That is one of those questions
like
that physicists
how I see it.
are really interested in answering.
How
but it's a fun
I'm seeing it is that if you divide opposing forces into time, then in a sense that is a nothing, right? Waiting to cancel out. So perhaps that's the answer to the paradox. But we either came from nothing or we never came at all. Like, at least in my eyes. But
I can't answer that at all. I mean, I am not.
Doesn't that make sense though? Like,
yeah, I'm not really.
If we said where did this come from, and then it's like, oh well, where did this come from? Like,
that's called the infinite regress issue. If the question is either something has arisen from nothing, or there's always been something.
Well, what are we talking about?
Lots.
We're talking about some kind of weird physical problem. It's not really physics, but it's
upon that subject. I want to ask you a quick question, man. Since you study the Big Bang and the beginnings, what is your biggest proof that the Big Bang actually happened?
We have two. We have the expansion of the universe, and we have the cosmic microwave background radiation. Those are the two. Do you want to explain why they are proofs?
Please.
Yes, please. Go, please. I love this stuff. Go ahead.
Which one should we talk about? The expansion or the microwave background?
The never proved expansion and the microwave background, please.
Okay, which one first?
Are you gonna go with the WMAP stuff from the microwave background, or
sure.
what? The WMAP satellite?
The Planck is later, but sure. We can talk about the measurement of the CMB.
Yeah, go ahead, please. Yes.
Well, I mean,
let's do that one first.
Okay, so the Planck probe is the most recent and most highly resolutive image of that. But we don't need to look at the WMAP or even the original one. The CMB ion itself, black body radiation. Do you know what that is?
Yes, I've studied black body radiations and heat transfer stuff, but go ahead. That was a long time ago. That was like 7 years ago. If you want to refresh my memory, that'll be
okay. I'll just go through it. If you have something which has a temperature, it's going to emit radiation. If it has a temperature, it's going to emit radiation. Not only that, but it's going to emit radiation which wavelengths are dependent on the temperature it has. Essentially, the warmer something is, the shorter the wavelength it's going to spit out. Right now, you're presumably emitting infrared radiation unless you're really, really hot or cold. I'm guessing since you're a mammal, you're going to probably be emitting infrared radiation, just like me. Twinsies. So that is the temperature of an object is dependent on this radiation. But we have different ways of having a temperature, right? Because if you ask somebody, what's the temperature of a car? In question, right? Because inside the cabin is a different temperature than, inside the wheels, and that's the different sense of the engine. There's lots of different temperatures. You're hearing me, right? Yeah, that makes sense.
Yep, I'm with you. That's
going to be different. Is going to emit different radiation wavelengths because it has different temperatures. So if you sort of looked at the car from a radiation standpoint, it's going to be quite complicated. There's going to be lots of different radiation coming out of it. The reason for that is because the car is too big to sort of transfer all the energy around itself. If you have rock and you can't heat that on one side without the heat spreading through the entire rock really quickly, because that's just how thermal conduction works. So if you take a little tiny rock and you heat it on the one end of it and leave it for a while, then it's going to have the same temperature everywhere.
Well, except the losses, or you're assuming a perfect environment where it's not going to have any, heat transmission or any heat transfer whatsoever.
Yeah, but this is just a thought experiment.
Oh, okay, all right, yeah. Heat one side of the rock, okay. Yeah, eventually, you'll transfer to the other side, yes, and it will cool off, or you don't want it to cool off.
It can cool off if you want, but it's going to have the same temperature all over the place. There's not going to be areas where it's hotter than that's pure statistics, really. You can't really
eventually.
Avoid that. You can allow it to cool off. Yeah, exactly right. When you have something like that, when you have something which has the same temperature everywhere, of its heat radiation is going to be really characteristic. It's going to make something called a Planck curve. It's a neat little sort of bell-shaped thing. And it's always going to have this exact curve. And that's what's called black body radiation. Black body radiation only occurs when the object has a consistent temperature over everything. So a car won't have black body radiation, but this tiny little pebble will.
All right. Okay.
The only way that you can have, because if we look at the universe now, I hope we agree that it doesn't have the same temperature everywhere. I'm pretty sure we agree that the Sahara Desert is hotter than where you are. You know, the universe has different temperatures, right?
Yeah.
So
you mean the universe as Earth, man? You kind of got me confused. I was looking up in the Alpha Centauri or whatever. It's like, oh, okay, what is he talking about?
The universe is everything. But I mean, I'm just saying, as a flat earther, not necessarily you don't have a universe necessarily. You just have the Earth. But no matter which model we have to agree that if we looked at the heat radiation of everything in the existence, there's going to be all kinds of different temperatures. Yeah.
Sure.
So that makes us really curious. Has there ever been a sort of a flash of heat radiation that emitted from the entire universe at once? And if so, can we see it? That's the big question. The great answer to the can we see it thing is yes, we can, for the beautiful reason that radiation cannot escape the universe. Once it's here, it's going to stay here because there's no way out. So when we have a flash of light from the early universe, it's got nowhere to go. It's still here.
Well, you're really assuming that there's no way out, though, right? Because I thought in infinity, I mean, it just keeps on going and going and going. Maybe the radiation has traveled further away, right?
Now you're assuming the universe is infinite, which you don't have any basis for. But
that's what they say in the science books, man.
An ever-expanding universe into infinity.
Exactly. Right?
Okay.
That is what we're discussing here, though. The cosmic, background radiation.
Philosophically, we can just philosophically
God bless you.
We can define it by simply saying the universe, by definition, is everything that exists. If we do so, then there is no way out, right? Because then we've defined ourselves out of that problem. If you really want to do it like that. So, in that sense, there is no escape. Actually, there's no escape. Heat radiation, no escape from the universe. I know, so dramatic, right? No, I can't get out. I don't really want to leave the universe. So I'm pretty cool about it, to be honest. So we have this. We can expect to see this light, but we didn't see it until the 50s, where it's a quite cute story. We had two radio astronomers who were trying to measure, and they had this noise, this background noise, which was really annoying them because no matter what they did, they kept picking up this noise, and they thought it was like pigeon crap on the antenna, and it turned out to be, the echo of the universe from old times, which was quite funny.
Or actually, microwaves being emitted from the water on Earth.
And they thought all kinds of weird stuff. They thought that they tried all kinds of things.
I've looked at the data from the WMAP and stuff like that. It's a joke. Like they keep on fudging it, or that's what they did. They kept on fudging it, until they got what they wanted, because the microwave noise that was being emitted from the water, because we know, right, what's a good absorber is a good emitter. Water absorbs microwaves quite well, and it also emits it quite well. So what they really got in the beginning is just this, they got bombarded with signals, like it's all noise. That's all they got. So they kept on just tweaking it, and putting correction factors, and correction factors, and correction factors, until they got what they wanted. Here it is. Right or wrong? Am I lying here?
Well, I'm misinformed.
Ooh, dude, you gotta look at the history of that stuff. The correction factors. When did those guys with the WMAP put that stuff in? Because all they were getting is just straight up noise. Nothing but noise. So they kept on fudging it. Like what physicists are good for. They fudge. It's called a constant. They fudge stuff. Oh, yeah, well, you know what? This is the result. Yeah, you're right. However, you got to multiply it by this. It's like, why? Well, so you get the result you want.
That's what I mean. That's not how it went at all. But that's okay. Can I continue my explanation?
Yeah, go ahead. I looked in the history of that. That's why I asked you about it.
I think you should look into it a little deeper, probably, and maybe find some sort of a little more sort of fair. But okay, we can talk about it later if you want. Okay. But anyway, the point is, we look at this radiation from the universe, which comes from every direction, and when we control for absorption in the oceans and all that kind of stuff, once we control for that, which is not a fudge, it's just basically making sure that we know that we're not measuring something which isn't the radiation from the universe. Once we get that fixed, and we know that we're not measuring something incorrect, then we look at it, and lo and behold, what we get is this perfect Planck curve, this completely beautiful, perfect Planck curve. I mean, the error bars on this thing are so small you can't even see them. It's just magically, perfectly a Planck curve.
After you got rid of the noise, correct?
Used a method which was consistent in getting rid of noise that we understood was there. Yes, that is not fudging.
Which wasn't actually noise, it was actually a signal. You understand that, right? That's my whole point. It was not noise. You know.
So what you're implying is that the WMAP data is faked. Is that what you're implying?
Yes, sir. Yes, sir. It's not by me, but other astrophysicists, and you know, they come out and said that straight up. You know, they did. It was fudge.
Straight up.
To fit their model.
I think you misunderstood them at that point. Fudge,
well,
to make the conclusion.
Yeah, fudge. That's what, you know, in science we call it fudging. We don't call it faking, right? We call it fudging. Right.
But you're implying that we're trying to get a certain conclusion, and then we just
we're trying to get that perfect curve. So we fudged it until we got it.
You're claiming that that's incorrect.
Man, I'm on my phone and I'm about to go to work. I swear I will look up for you when they exactly did this and how they did this.
Please do. We can talk about it later. But the point is that it shows that the temperature of the entire universe was uniform. That means that everything in the universe is everything else, and that is only possible if the universe was extremely hot and extremely dense. Looking down to the Big Bang, there's no way out of that. You cannot avoid this.
Okay, I think that from that point we can probably move on. Dem, did you have something you wanted to add or move on to?
I can move on to anything.
All right. Maybe let's talk about the shape of the Earth. What gives you the best evidence, Robert, that you could give us that the Earth is a spherical shape? What's your best
geometry
evidence?
of the horizon?
The geometry of the horizon, you say?
The word based on horizontal.
Robert, did you say the geometry of the horizon?
The geometry of the horizon.
What about the geometry of the horizon?
The horizon is acting exactly.
What about my geometry on my horizon?
Hang on, hang on. What was that, Robert?
Just saying that the horizon that we observe completely comports with the horizon in the sphere.
Really? Yes. How would you go about doing that? Can you please walk us through the evidence of that?
Of course. Well, let's define what a horizon even is. We can actually give a horizon to any object we want. Okay, it doesn't have to be the Earth.
Let's talk about our horizon. We're the ones that are looking. Let's talk about the one that we perceive.
No, we're just talking about what a horizon even is. Okay, because if you have a hill,
everybody understands the horizon is the limit of your view.
Yeah, let him explain it. Cyclone, please let them have this discussion.
Yeah, sure.
So if you're looking at a hill, now we're going to get back to the Earth. I promise you. Just let's put the Earth in the box for now, and we're going to come back to it. Let's just understand what we're talking about here. So we're looking at a hill, and we can have it on a flat Earth if you want. I don't care. We're looking at a hill, and the edge of that hill is the horizon of that hill in some sense. Because what a horizon is the line of sight, the tangent line to the object. It is basically the lowest line you can make from your eye to the edge of that thing, and you can't look behind it. That's what the horizon is. That is what a horizon is.
Okay.
Now, the thing about...
Hold on. One quick question. So is this horizon going to cause obstruction? Like physical obstruction? Like if I were to try to shine a laser through this horizon, would it go through? Or is it the leading edge of the sphere Earth to you? Or is it an apparent horizon where it's a visual optical horizon?
You cannot see beyond the horizon.
That wasn't my question. My question was, would I be able to shoot a laser through this horizon? Or is it an apparent horizon? Or is it the leading edge of a sphere where it's a physical horizon?
Asking me if it's possible to get a laser beam on the other side of the horizon from where you're standing. Is that what you're asking me?
Yes.
No, you shouldn't be able to do that.
Said no.
Choose carefully your response.
It's a very simple question. Can you yes or can you not? I mean, is it the leading edge of a sphere? Like it's actually like a physical place you can land on? It's the horizon, or is it an optical illusion created by the eyes?
It's not an illusion. It is the points on the Earth that are the furthest away from your eyes that you can see until the rest gets obscured by the shape of the Earth.
Okay, so we should
beautiful.
see things past the curvature, right?
Guys, I want to build on it. I was built into something. Hold on. All right, wonderful. So now you agree that like I wouldn't be able to shoot a laser to that because it's the curvature of the Earth, in other words, right? Right?
Yes.
Okay. So here's the thing. Here's the problem with the globe Earth model. When a globe Earthers see the horizon, they do call that the leading edge of the sphere. Or when they see any type of obstruction by that horizon, they call that the leading edge of a sphere. Now the problem is that when we actually go out and do measurements with lasers, high-powered lasers, a 0.8 millirad laser, about 2 meters above sea level, doing a horizontal pan from 6 kilometers, 12 kilometers, 41 kilometers. All target heights are 1.5 meters of height. Use the WGS84 model, which is the oblique spheroid model. We get that the shortest target at the furthest distance of the 41 kilometer mark should only be 90 meters. And if we added a 7.6R standard refraction, it'd be 85 meters. But these people are hitting 1.5 meter targets. So the problem is that we see what you think is curvature. Everyone could see that horizon. But when we actually go out to directly measure it over water, we don't get that horizon whatsoever. We don't get that obstruction. We can literally draw a tangent line between 2 points and hit it. So there is no measurable curvature on Earth. It's only optically induced by people when they see obstruction or a horizon. But when you go out to measure it directly, there is no curvature whatsoever.
Do you have a concrete measurement? Do you have an actual data point here?
Absolutely. I'll send you the PDF. Yeah, I'll send you the PDF right now. 1 sec.
Let's just take one measurement at a time. So let's just have a look at one.
It was actually 3 measurements. It was a horizontal pan. Picture like the laser being leveled, and then they hit their first target, which is 6 kilometers, and then they horizontally pan it to the next target, which is 12 kilometers. They pretty much survey those 3 points with the laser by doing a horizontal pan, and all target heights were the same height. You know.
Okay, so wait, we have a 6 kilometer distance, and we have 1.5 meter height.
Yeah, the target was 1.5 meters of height. Correct.
What is the elevation of the laser itself?
2 meters. And the divergence of the beam for this distance is about a 2 meter spread beam because it's a 0.08 millirad.
Have a look at that. 0.8 millirad. That's going to spread quite a lot over 6 kilometers. Let's just, I'll check that. But okay, yeah. Is it 2 meters over sea level?
2 meters above. Correct.
Sea level, not over ground, but over sea level.
Oh, yeah, from sea level.
So we're actually at the ocean doing this.
You mean over sea curve, bro?
It's a lake. They're right over a lake.
Which lake
I'm posting it. I'm posting the whole document, the whole document for you right now in voice text for everyone. It's called FECORE.
I've seen this before. So this is Lake Balaton, right?
No. This is all of them. Lake Balaton, Lake Hungary, Sweden, Lake Issel.
Which one do you want to look at? We need to take a particular.
I was talking particularly about Lake Gisel, which is the 41 kilometer distant one.
We just find that one. That's the Balaton one. Just hold on. Okay,
yeah,
the ISIL one. It's
ISSEL, yeah. ISSEL, Lake Gisel.
This is Dutch. Dutch people have weird ways of saying things, so ISIL is the pronunciation.
Yeah.
Who cares about that? So we have Lake ISIL is presumably pretty low. But let me have a look at what the elevation of Lake ISIL is. Just hold on. We need to have the actual answer. Okay, it's the surface elevation of ISIL is about. That's fine.
Hey, Robert, I was just. Forgive me. I was just curious. Is this the first time you've seen this?
No.
What Jose sent you?
I have seen.
Is this the first time you've seen
measurements before, but I haven't looked into them yet. So this is kind of fun to have a reason to.
Okay.
So anyway, we have the Lake ISIL things here. We have a target position here. Let me see what it says. It says that we have a blue laser placed 2.85 meters above the lake surface, and it was seen on the opposite shore at 21.26 kilometers to target 1. At 1.2 meters. That is on page something. I'm sorry, I can't see the page numbers on this viewer. this is measurement 3, Lake ISIL target 1. Is that okay with you? Did we look on that one?
Yeah, I'm looking at it too.
Okay, so we agree that that's the one on the 8th of April at 1 a.m. That's the one we're looking at, yeah?
Yep.
Okay. So let's have a look. We need to figure out what you're claiming is that this is impossible on the globe Earth, essentially, right?
Yep. Absolutely. 100% impossible on the ball.
That's your claim. So we have a 0.8 millirad spread. Do you understand what that means? What 0.8 millirad means?
Spreading.
You actually calculate that.
I have some like
it's about 1 meter.
19-year-old kids here I want to sacrifice, you know. In which channel do you turn?
Sorry, what?
Oh, God.
I'm joking.
What?
Though.
No, I just didn't hear what you said.
Yeah, it's about 1 meter.
You're trying to make a joke. It wasn't funny.
I didn't catch it, I have to say. So the first thing we need to figure out is how much the spread actually is on 0.8 millirad, yeah?
Sure,
so,
it's 1 meter.
No, let's calculate this. I have 0.8 millirad. Do you agree that is the same as 0.045366 degrees? You are welcome.
No, he said 0.08 millirad, I believe, not 0.8 millirad.
So 0.08, okay.
0.08.
Well, I would want Jose to double confirm that.
Yeah, it was a 0.08 millirad. I don't ever say the first zero. I always go with point. I start with the point, so it's 0.08.
They didn't say the size of the aperture coming out, though.
We'll get to that. So we have, that gives us a spread of 0.00458 degrees. Do you agree?
Yeah.
So we just need to figure out what that means. Do you know, Trig, enough to do this?
Yeah.
Oh, yeah.
We're just going to make a little triangle here. I can't do a diagram, but I'm sure you can figure it out. The one point is at the laser, and the other 2 points of the triangle is at the edges of the spread beam. Yeah?
Yeah, you're going to use tangent. Yep. Inverse tangent. Got it.
That seems meaningful. We have a distance of 21.26 kilometers. We don't know the spread, so it's going to be something like the tangent 2x over 21.26 is half that angle. Yeah?
Yeah.
Spitballing that. So let's just solve that.
Yeah, that's right. We don't know what the aperture is. So we don't, we know what spread is, but we don't know what the initial aperture is.
But we guess it does say what kind of laser it is, though, so we can check that afterwards. But let's just figure out the spread, assuming, for friendliness sake, that it starts at a point. But of course it doesn't, but we'll try. So we know that. And we know that this angle is 0.002 something. Okay. I'll just do some math here. Live on air. Isn't that exciting? So we have the half degree, 0.0229. I know, it's incredibly exciting stuff. So we need to do inverse tangent of that. Hold on, arc10.
0.9 meters.
Let me have a look. This is how we do things. So that means we have 0.02. Okay. Hold on. That by 21.
It would have been easier if you just used a calculator online.
That's what I'm doing. I'm
calculating this from. I won't bother you no more. Sorry.
I'm going to get a reasonable calculator here. 0.002. The tangent is equals to, well, hold on. Tangent to the angle. I'm being really slow at the moment. Just hold on a second. Okay, we're back. A little bit annoying. I apologize. So, Google, you suck. Okay, so that gives us, gives us a half spread of 0.09 kilometers, apparently. 0.09744 kilometers, which is 9.7 meters.
That's a huge spread, isn't it?
It really is. Do you want to do do you want to run through the math with me, so we'll make sure that we're agreed on it?
I'm gonna fucking smash that.
No, I'll actually be more than happy to give you the 90 meter spread because that's still not enough. So go ahead, take it.
We'll take 10 meter spread just around. Is that okay with you? just to
That's
make
fine.
it easier. Okay. So now that means we also have an aperture, as it's been pointing out. We need to know the initial size of the beam, because that's of course going to be spread out. We are assuming a point-sized beam. So this is the blue laser pointer, it just says. So we need to know something more about what this laser pointer is. So let's go looking in the documents. WGS84 laser? No, that's not right. That's not the one they use. That's a target correction thing. Anybody got a clue of what it is?
Yeah, they didn't actually list it, the brand or anything.
I'm guessing we need to assume a basic. I mean, it's going to have a pretty good range, right? Do they mention the power output of this thing?
They do. I have to go through the document. It's been a while since no one's really looking for that.
You can just assume, man. You can, give it a couple of millimeters or a few millimeters, 5 millimeters, whatever. You can start with the point, and then you can do another calculation with the, whatever beam width you want, as long as it's within reason, right? A few millimeters or so. Or I don't think it's going to have a 1-inch beam to begin with.
Oh, it's going to be.
It could though. It could. I don't know.
I mean, the thing is, if it needs to reach 21 kilometers, it needs to be a pretty solid laser. I mean, it's going to be 200 milliwatts or 400 milliwatts or something like that. I mean, otherwise you're just not going to see it.
I think it's pretty
there's
expensive.
actually pictures.
Yeah, it might be a really nice laser.
I can imagine it is. If you want to, are you kidding me? This is a great toy.
That's a good laser.
Especially blue lasers, because they're quite expensive. Actually, the green ones are way cheaper. You can buy them.
But the blue ones are the most effective, I think, for long range. Correct me if I'm wrong.
Blue gets scattered less, or gets scattered more actually.
So it's the green ones then, either green or blue, one of those.
I think blue gets scattered more. I think I think so, Robert. I'm not totally sure.
More on the blue, yeah.
Right.
All that.
I'm back, guys.
I mean, you have to have a really solid case before you try anything,
Right, let's have a look at the expected curve, shall we? Just have something to do while we're looking for that thing. So, what did you say the distance was? 21.26 kilometers, yeah?
No, it was 41 kilometers. The furthest distance.
We are looking at we agreed to look at the measurement of.
The furthest distance was 41 kilometers.
Yeah, but
which is about 25 miles.
You know what?
Yes, but we agreed to look at the one with 21.26 because that's the one I did the.
I agreed to look at the 41 kilometer one, which is the furthest distance.
Yeah, but then we need the longest one. Let's do the longest one.
Sure.
Yeah, because
hold on. That means we need to do a new calculation of the divergence because I did it based on 21.26.
All you got to do is look at that document and tell me what are your targets, because there's no pictures of the targets.
No.
Hey, Busted, we talked to you about this last time. Let Robert handle it this time, all right?
Sure.
You're kind of just interfering now.
Let's just have a look. It's just having fun. Red's rhetoric? I feel honored. Okay, let's have a look. So we need the one. Which measurement is that then? This is the one that's called the.
Latest kilometers furthest distant.
Measurement what? Measurement 5? No, that's not long enough.
Yeah, let's go grab it for you 1 sec.
I have here.
6 to 7.
Yeah, there we go. 40.14 kilometers. Yes, that is the 22nd of April at 2:19 a.m. Do you agree? This? Is that the one?
Yeah,
you
1
want to look
sec. Let me just double check it.
It is. That's measurement 6.
We good?
That's correct. Measurement 6. What you said.
Yep. So that means we need what was the measurement again? It was 40.14 kilometers. Yes. Okay. So from a point laser, there's a divergence of 18.39 meters.
How are you calculating the spread?
Starting from a point source, that is being very generous because, of course, it's not a point source. Then I'm looking at it as a triangle where the one point is at the laser, The two other points are at the upper and the lower edge of the spread beam.
The spread. That's a good question, though. Yeah, like a V-ray, like a shooting engine, you know, with all the lights and stuff.
Imagine a V-ray that just stops at 40.14 kilometers, and that gives us a triangle, right?
Okay.
And we know
Fair enough.
we know that the small angle of this triangle is 0.08 millirads, because that's what's been told us in the document, and that gives us all we need to know, because we know the distance, we know the height of this triangle, because that's 40.14 kilometers, and we know that angle. So by doing that basic trigonometry, we get that the spread is 18.39 meters. I can run through the calculation if you want. We have an 18-meter gap, which we need to realize at least, based on a point source. So it's going to be bigger in real life.
Can you type out like the math you're doing? Because I want to double check, because I don't know how the hell you're getting 18 meters of spread.
10 of 0.04 millirad.
No, type it out in the voice text for everyone. Type out your whole math equation so I can see it, because I don't know how you're getting that spread.
That is what I'm doing. Do you want just the calculation, or do you want the I'm calculating from? And then we need 2x as the spread. Do you see that?
Let me see. One sec. So why are you putting a 0.04 millirad?
If you imagine that V-ray, you have to divide it into
we don't have to. We know the millirad. The millirad is 0.08. You're cutting it in half.
Yes. Now listen.
Why are you doing?
Because we want a right angle triangle, because that's easiest to calculate this, and we just simply split that V-ray into half. That means that the angle gets halved in the middle. Yeah. The opposite edge. Yeah, when we're talking about we have this ray coming out of the laser, and it's spreading as it goes. Up it at 40.14 kilometers, then we get a triangle. Drawing in here somehow? I don't think I can, but
I mean, like in V-ray, you have to bounce from something, you know, to another, you know. The ray has to bounce, you know. So I mean, if you end up with a triangular shape, it's your problem, you know. It's not mine.
We're trying to. Okay, you have a beam, right, and it has a certain size. Do we agree on that? Do we also agree that the further we get from the laser, the diameter of this beam is going to grow? Yeah. Make sense? The diameter of the dot that we are seeing is going to grow.
Yeah.
Okay. So the diameter of the beam is what we're going to call, that's what I call 2x. That means that the radius of the beam is just x. Of the beam out to the edge. That distance is going to be half the angle of the spread, 0.04 millirads, to get the radius, as opposed to the diameter. And once I calculate that, I can multiply by 2 to get the actual spread.
If you're not spreading, is it by default double the angle, you know?
What I'm doing is I'm just making, we can do this, we can calculate it without doing all this halving. This is just basically an easier way to do it. If we have to do it the other way, we're going to have to use the law of sines. You can use that as well if you want. It's just a question of which triangle calculator you're using. If you prefer, we can just go into a triangle calculator and just do it. But then we don't see that the math works. I feel like we should
just
actually do it ourselves, right?
That's Nike said.
You can go into a site called costsincalc.com. I'll just give you a link, and you can just type everything in there if you want.
No, seriously though, I'm just messing with you, you know. But is this like a V-ray calculation, you know? Because I find it amusing, you know, interesting.
It's the calculation of how
listening. I'll read you from the from a book called 13.8. The Quest to Find the True Age of the Universe by John Gribben.
We're talking about something else now,
I'll start off with
The Big Bang, I guess. Yeah.
No, it starts off introduction. The most important fact. Now, get this. This is the fact, right? And the origin of everything we see about us, stars, planets, galaxies, people, can be traced back to a definite moment in time, 13.8 billion years ago. Now, that's a fact. Is a heretic. Fact, okay? Theory.
Which book are you reading from here?
Let's not argue then.
13.8, The Quest to Find the True Age of the Universe and the Theory of Everything by John Gribben.
Okay, so what's your point?
It's a fact. It's a fact. The universe is 13.8 years ago old.
Right, billion
years old is a fact.
According to him, sure.
Because John said so. Or
this is what you guys are selling to the public. This is what you're selling.
What distance are you guys solving for the spread? What's the distance to the object? The 41 or the 21?
This is what's peddled out to the public.
14?
It's sort of fact.
You said?
Lies.
Robert?
I don't really care what John Gribben writes. We're going to calculate this stuff now instead.
Yeah, what's the distance to the object that you're using for the spread? Calculate the spread.
40.14 kilometers.
Okay, 40.14. Okay, cool. Gotcha. Thank you.
So, are we good with the spread?
I'm still trying to figure it out, dude. Give me like 5 minutes, all right? Give me 5 minutes. I'll be back.
I'm gonna run the math myself right now.
I'm trying to figure this out, dude, because I don't know how the hell. Like, I think it's kind of strange that you're trying to cut the millirad to 4 and then add it later. I don't know. I think that's kind of just messing it up for me. It's confusing.
He's just dividing the triangle in half, Jose. So he's solving for the like a 90-degree triangle to make it easy. So he doesn't have to use the law of sines and cosines.
Exactly. I can use the law of sines instead if you want.
Right.
It'll be the same result. I'm being lazy. But anyway, while we're waiting, 5 minutes, I'm happy to talk about something else.
Excellent. Can we talk about space? Is that okay? Can we talk about space?
Sure, as long as we get back to this FECORE thing.
Yeah.
I'm fine.
5 minutes, I mean, you have a quick chat about space, yeah?
Sounds good.
Excellent stuff. So you're really into space. Obviously, it's your job. It's what you do. You look at lights in the sky and tell us what they are. That's brilliant. You've obviously been talking, as you said, you've been talking to quite a lot of flat earthers over the last however long. So you've obviously come up with the thermodynamic problem, air pressure and vacuum, yes?
I've heard that before, yes.
Yeah, so we are breathing air pressure said to reside within a vacuum with a vastly lower pressure system. So thermodynamic, when we're talking about energy transfer, especially air pressure, the air pressure would fill the void unless acted upon by a physical container. Where we have air pressure, we need a container. Unless you start asserting unless you start asserting two gravities, both of which you have no scientific evidence for. So what is your retort to this issue?
We are not in a pressurized system because the pressure drops when we go up.
That's a pressure gradient, though, isn't it? Still a pressure gradient, still has press in it, still needs to press.
Pressure gradient goes
it's
to
a pressure
zero.
Gradient. Sorry?
Pressure gradient goes to 0 and then you're in a vacuum. There's no problem.
No, nothing's pressure. Yeah, we have an air pressure. It should fill the void. That's what it would do. Exactly what it would do. Just because we have a pressure gradient doesn't negate the air pressure needs to press upon something.
Well,
Does
if
it?
that were the case, then there should not be different air pressures at different heights. So you're missing something.
Why not? We have different gases. We have different gases. We have energy coming into the system. We have a dynamic pressure environment, a dynamic weather environment, a dynamic environment all told. We have different heat sources around the world, all different types of things. Yes, we have a pressure gradient, but the necessary antecedent for a pressure gradient is something to press upon. So the air is not going to the air is not going to contain itself unless you would like to demonstrate to me gas pressure without a container.
So you claimed that the reason that there is different pressures at different heights is because there are different gases, right?
Different gases, different pressure, yeah, loads of different things. So loads of different things.
The problem is that's not true. It's the same atmospheric, composition up a mountain that there is down here.
Yeah, and you go higher up into the atmosphere and you get different gases. And I'm not saying it is not a pressure gradient. Of course there is, but that's got factors to do with moisture in the air and temperature. And obviously it gets colder the further that you go up. That's why we have snow on the top of mountains. My point is this, regardless whether it's a pressure or pressure gradient, that pressure still needs something to press upon. It's not just going to shade out and eventually reach zero and turn into a vacuum. The gas would fill the space.
That's a claim, and you're wrong.
It is.
Let's just put that.
You're just going to say that I'm wrong. You are literally going to fly in the face of the second law of thermodynamics and say that I'm wrong. I'm quite surprised you haven't turned around and said gravity yet.
Of course, it's caused by gravity, but the fact is that this is
which one? Which gravity is it caused by?
Gravity that exists.
Which gravity is it caused by?
There is only one gravity, my friend.
And which gravity is this?
Robert, did you say that there is a place in space with zero pressure?
I said there's a vacuum. I'm not saying there's a perfect vacuum.
You say there's somewhere in space that has zero pressure?
Zero, but incredibly close to zero.
You say there was somewhere in space with zero pressure?
No, there's no space with zero pressure, but you get something which is so close to zero that it doesn't matter. Anyway.
But you said that. You said there was a minute ago. I heard you.
Fine, but that's an approximation.
You said it goes up to zero pressure.
That was an approximation because there's practically zero pressure, but thank you for correcting me. Anyway, yes, it is gravity.
No.
Do you want which gravity?
Yeah, which gravity? You just tap Chad. I'm going to do it again in a minute as well.
Hey, Robert.
I'm
sorry. Please, can I finish this conversation, guys? Please.
Oh, for sure. I'm sorry. I didn't mean.
No problem. No problem. Because I've just been told there's only one gravity. I want to know which one that is.
Ooh.
Yeah, we're talking about. I'm assuming you're referring to the Newtonian model of gravity versus the Einsteinian model. Is that what you're doing?
Don't know. You've just there's only one. So which one are you talking about?
I'm talking about the effect that we see. We see that there is a force. We can take it as a force. You can describe it as a space-time curvature if you want. It gives the exact same results. But let's just keep it simple and describe it as a force. And we do see there is a force.
Sorry, they're mutually exclusive. One's in 3D space, the one's in 4D space. Mutually exclusive.
It gives completely
yeah, because things fall down. So yeah, we have the exact same result. Doesn't matter which idea you come up with. Yeah, things fall down.
And also air falls down. Therefore, there's a pressure gradient.
Yeah, we have a pressure gradient. Yeah, it should disperse into the vacuum. My question is this: what scientific evidence do you have for, this gravity that you're asserting? What's your scientific evidence for it? Because you need it to negate a natural law.
And things fall down with an accelerated speed. That's why.
Yes, hold on. Hold tight. I said scientific evidence, not a mathematical calculation of things going down. No one's disagreeing with you that things fall at a certain rate. I want your scientific experiment proving your gravity. Very simple. I want your maths.
That you need a force to create an acceleration. Is that
no. I want your scientific experiment. I mean, when we started talking an hour and a half ago, 2 hours ago, did have to tell you the scientific method and tell you how you weren't doing it. So now I would like your scientific experiment that proves gravity, not that things fall down at a road.
I have one experiment.
Just one scientific experiment, hypothesis.
So
first we need to. Okay, please go ahead.
Okay, thank you. So you know Neptune, the planet, yeah.
What?
Neptune, the planet. You know what? You know Neptune.
Neptune.
Yeah.
Why the fuck are we talking about Neptune now?
coming in throwing googlies about Neptune. Get out of it.
Go ahead.
So
Dan.
let's go back to the
scientific experiment that proves gravity. I don't want maths.
Okay.
I want your scientific experiment that proves.
Okay. So do you accept?
You know you haven't got one, don't you?
I know I've got one. I just don't know that you're going to listen to it. That's a different question. Do you accept measurement of acceleration as a measurement of force? Yes or no?
Sorry, I've got something in my mouth. Don't mean to be rude. I don't want to talk with my mouth full.
It's fine.
I agree that you can calculate how fast things will fall, depending on their relative, I don't know, density falling through a medium, for example. So if I was to drop a ball through the air couldn't support it, so the ball would drop. But if I was to let go of a helium balloon, helium obviously being lighter than air, it would rise. So yeah, I would agree. You can use a little bit of math to calculate how fast something is going to fall through a relative medium. But I'm not asking for your math. I want your scientific experiment that proves cause of an effect.
Let's try again. I didn't mention calculations at all. I asked you, do you accept a measurement of acceleration as a measurement?
And I expanded on that. So
we did not accept a measurement of acceleration is a cause of force.
Yeah, exactly.
Do you accept the measurement of acceleration? Do you accept that we can measure acceleration?
Measure acceleration. What are you talking about?
Do you accept that acceleration of an object can be measured?
We can measure things.
So you can measure acceleration, right? We're not calculating anything.
Yeah, you can measure acceleration, yeah? What?
Yeah.
Is that an effect and a cause?
Acceleration is caused by a force.
Okay, can you prove that force?
Just asking
what's causing the universe to accelerate outwards? What's the force?
Let's stick to one thing at a time. Do you accept that a force?
No, you said there's is the universe? Yeah. Well, I'm giving you an example of something that doesn't require a force to accelerate.
Maybe you could give us an example of what is relative to. So, dropping something relative to a non-stationary moving plane, right? Or two cars are going at 60 kilometers an hour, and then one car goes 70 kilometers an hour and passes them. Like, we could measure that, but so what would gravity be measured in relation to what? Like, maybe
we're getting to gravity, but we just need to make sure that we actually accept these measurements.
Here's the thing: we accept that things accelerate at 9.8 meters per second squared. What's the cause of the acceleration is what we're debating.
That's a great question. But you accept that there's a force then. That you accept there's a force.
Oh, we do not accept there's a force.
My God.
You accept acceleration, though.
Yeah, but we don't know the cause.
Lovely.
Einstein said it wasn't a force. Now shut up.
Yeah.
By the way, your math is pretty shoddy, bro. I ran the math. It's only 3 meters. Total divergence is 3.15 meters at 40.14 kilometers. Your trig is way off. And I snapped a picture of it and posted in voice text for everyone, so you can double check my math yourself. I mean,
I think you used 0.04 degrees and not rads. I think you made a
no, I converted. No, buddy, I converted the rads to degrees, man. What are you talking about? I used 0.04 millirads to degrees. Okay, and then use the tan of that, the tan of x over 40.14. Go ahead, just check my math yourself, please. I drew the triangle. Let me know what I did wrong.
Just check it again. Hold on.
Well, what I think can happen with maths is, considering it's a language and there's different ways for people to learn said language and then being taught said language, it's like saying I write out do not and you write don't with an apostrophe. I mean, that's really what it sounds like is happening.
Nope, that's not what's going on. So what do you get the tan of the angle to? Just alone, just the tan of that half angle.
I got you. Okay, the half angle. How much is the half angle, right? All right, so I'm gonna just go millirad right now. Mrad to degrees.
I think you're right. Hold on.
Yeah, it's 0.00225 roughly. An estimation. That's the half angle.
I think I have used
Did you?
It seems that you have to type degrees to make it calculate in degrees. I do apologize.
Can you see my work? I took a picture of my work and I posted in voice text for everyone. Can you see it?
Yeah, and you're right and I'm wrong. I calculated using Google calculators, and I simply used you have to type something in. I apologize. You're right.
No problem. Thank you, sir. It's not a right or wrong. I'm just saying, clarifying for everybody. At 40 kilometers, the total beam divergence from a point source, yes, I assume the source is a point, is 3.15 meters.
Accept this. Cool.
All right. Cool. Carry on.
Are we talking about the divergence thing again? Or are we talking about the force?
Wait, I think Dem had a point.
Yes, you can go and talk about the divergence beam because you are not going to give me a scientific experiment, are you?
Okay. Oh, you're not going to listen to it, so that's probably
Jose said he needed 5 minutes.
Hold on, don't dismiss me, my friend. I'm going to let you carry on and talk to these other people, but you know, intellectually, honestly, that there are no scientific experiments that prove either of your gravity ideas unless you start asserting math. Now, you know that.
Don't, because we can see, objects directly.
This isn't a scientific experiment, though, is it? I mean, if it was, it would be an adherence to the scientific method, wouldn't it? There would be a naturally observed phenomena, wouldn't there? There would be a hypothesis where you presume your cause, wouldn't there? You could then go and do the experiment, wouldn't you? And then you could validate it, couldn't you? Yes, so you don't have a scientific experiment, do you? No, then exposed, I don't.
Well, you can deny it all you want. It's fine. It's just I do. It's quite simple.
Yeah, no, it's fine. But the thing is that you don't have a scientific experiment that proves gravity. So therefore, you can't overcome the second law of thermodynamics with something you can't prove. You just assert it to be true without actually any evidence behind you. Just a little bit of maths because things fall down. That's my point. You can carry on talking about your laser test now. Now somebody's corrected you on your math.
Okay, so let's go back to the laser test.
All right. Jose, where you at, man? You said you needed 5 minutes. Granted, sir. Math solved. All you, bro.
Okay, so it was.
I'm going to do a 5-minute warning here too. I'm sorry, I really have to go. I'm not trying to run away.
Yeah, that's fine.
I can come back and talk about all the rest of it later, but I do have a life as well. So let's just do the last 5 minutes on this divergence.
Okay.
So we found out that we have a 3.25 meter.
Yeah, it was about
at the end of this.
Spread.
Okay.
I said 2. I was close.
If we assume a point source.
Right.
Agreed.
So now where are we at? How does that work on the oblate spheroid model? Even if it's the WGS84 model, which predicts that the shortest target you can hit on that oblate spheroid has to be 90 meters. And if we gave you the 7.6 art standard refraction, which is being generous to you, it shaves it down to 85 meters. How are we hitting a 1.5 meter target from that distance with the beam divergence being 3 meters?
Oh, am I back again? I hear nothing.
I could hear you. You're good.
All right. So, as I say, did you hear my 5-minute warning that I have to run? And I'll come back if you need to talk to me. Okay, cool. So we are agreeing that we have a 3.5 meter divergence.
Yep. 3.15. So just call it 3 meters.
Okay, cool. And if we look at the measurement, it says that the blue laser points were placed at a height of 2.92 meters. Yeah.
Yes.
Okay, great. That causes a problem because we can now calculate at what distance the laser beam will strike the surface of the water. The 40.14 kilometers, yeah? Because the divergence is more than 2.92.
Can you go more in depth on that? How would that be a problem exactly?
Because then we have reflection off the water.
Yeah, but where would the reflection be? Think about that. This is 41 kilometers I'm speaking of.
It'll go down on the surface of the water, then it'll bounce off it at the same angle. And that means we can measure it the direction as we expected it to be. There's one issue that I'm just pointing out would be a problem here.
Again, that's the full beam width at 40 kilometers. The full beam width would be 3 meters. Okay. All right. Assuming a point source. All right. Cool. And we are roughly 3 meters above the ground. So that's centered. You got to divide that 3 by 2. So you'll be only 1.5 meters from the center of the observer height to the water. Thus, you would. So, what's the height of the object? 2 meters above water, or what was that?
2.92.
I don't know. I don't have the paper in front of me. But you assume the full 3 meters. You got to take the half of it, bro.
Of course.
Right? Because you're dealing with it with a conical beam, half triangle again. Yeah. So it'd be only 1.5 meters.
I get that. And there would be no issue if there was no atmosphere. But now we have atmosphere, which means diffusion, which means refraction, which means all kinds of things. We're getting pretty damn close.
Yep. Yes, exactly. We're getting close to touching the water, but we did not. We did not.
You would not touch the water if there were no atmosphere. But you have diffraction in the atmosphere.
Here's the thing. We've already assumed 7.6R, which it's not the 7.6R refraction you're going to invoke. Give me what refraction model you want then. Because even if we use your 7.6R, it goes down to 85 meters.
I'm going to invoke scattering.
And now the refraction you're talking about, there's obviously meteorological data. You can take a look at that. It's in the PDF. Took temperature, pressure, tide levels, everything's in there.
But I'm
so yeah, like all that is taken into account. It's not like it's not taken into account. And I'm even giving you the generous Mick West curve calculator, the Metabunk one, the 7.6R. So like, you saying refraction isn't changing the results?
I'm asking you.
Jose, let's give him this. What if the beam actually touched the water, and now where is it shooting? Around the curve or up into space?
Would bounce off at the same angle.
If the beam hit the water, I would be absorbed. Like it wouldn't so much reflect to the target. Be impossible, in my opinion, especially on a globe.
Let's assume the water is a mirror. We'll give him another one, Jose. Water is a mirror. It's going to reflect. Where is it going to reflect to, bro? Around the curve or up into space?
Okay, listen. That is the whole problem. The water is definitely not a mirror. It is not a specular highlight you're going to get.
You said it's going to reflect. That's why I gave you the mirror, man. Of course, it's not going to reflect like that off the water.
It's going to reflect off all the angles that it can get. It's going to reflect off all the angles it can get, which means some of the light is going to be thrown downwards. In space, and it's going to be thrown downwards. That's how a diffuse reflection works. So we're going to easily get. But have we taken diffraction? No, sorry. Have we taken scattering into account? That's what I'm asking. You're saying that they've taken refraction into account. That's great. Have they taken scattering into account? Atmospheric scattering, Rayleigh scattering.
I do not have the PDF in front of me. Actually, I never actually took a look at the PDF. I just know my math. Know my trig works. Trig is solid.
I just need to know how to use the calculator I was using. That's quite embarrassing. But
yeah, that's why I go old school, man. Paper and pen.
But I'm glad that you checked me because that's the whole point. But we have a measurement 6. We have stuff like the vacuum wavelength. We have the air temperature, humidity, wavelength, refractive index, all that kind of stuff. But we don't seem to have any scattering taken into account. So we need to look at the Rayleigh scattering of this beam.
Okay, but before actually look at the scattering, you have to run the math on this. At 40 kilometers, let's just call it 40 flat, 40 kilometers, what distance below the curve is this object supposed to be?
I checked it while you were gone. I can't remember.
How many meters?
I can't remember. It's definitely below the horizon, clearly.
How many meters below the horizon? Of course it's below the horizon. How many meters?
Let me just check again. I can't remember. It was very clearly below the horizon.
For that, you just use a calculator off a Metabunker.
Yeah, I'm going to do that. Yeah, I'm not going to do the math there. I'm just going to use the math. Okay, let's say 40 flat, as you said.
Yeah, let's call it 40.
And we have 3 meters in height, I guess. Then we have something with refracted hidden, something like 74 meters.
Awesome. 74 meters.
Yeah.
And the total beam width is 3 meters at that distance. Okay, total beam width is 3 meters in a conical shape. Okay, above the surface of the water. As we said, we're getting close to touching the water, but we did not touch it actually. All right.
Well,
see what I just posted? Hold on, guys. I just posted this for the document. It's 90 meters. What we're talking about.
Well, according
to that document, at the end of the document, there's technical data you can look at with details of what
that's without refraction
is.
Oh, thank you. I'll check that later. But anyway, you're wrong if you say that it doesn't touch the water. It definitely touches the water. It only does not touch the water if there is no atmosphere.
It's awesome. Does it bend around the curve?
Definitely.
How does it touch the water?
Because you have scattering and you have refraction. It's definitely going to scatter.
Yeah. Are you going to claim that the scattering that's water is the light that's being seen from 41 kilometers? Is that going to be your next claim now?
You need to look at the picture because the smoking gun here is the target for observation location. You need to
No
look at
one's
that.
denying what you're saying, but it sounds like it's not a good excuse to claim that that's the beam that they're seeing. They're seeing a direct line of sight.
So it's scattered downwards around the curve to hit the object 70 meters. I'll give you your 74 meters. Okay. So it's scattered 74 meters downwards.
Of course, it's bouncing off the edge of the water and it's being scattered in all directions. But if you look
all
at
directions, so we're going to lose intensity.
Evidence that light. So here's the thing: like are you claiming it's refracting or scattering? What's the difference between scattering? I'm not that familiar with scattering. Like, you mean the light? How like it bounces around? Do you mean that type of scattering?
Losses to the atmosphere.
Robert, you talking about the Rayleigh
to the molecules or whatnot.
I answer it, or are you just going to yell at me? The scattering happens when you have polarly charged molecules in the atmosphere, and you have Rayleigh scattering, which basically means that it's absorbed and re-emitted, and it gets scattered out in different directions, and it's wavelength dependent, strongly wavelength dependent. And if you look at the picture, which is called target,
isn't that scattering going to diffuse light source a lot, like big time diffuse it?
Yeah, all light sources get diffused by this.
Exactly. So what we're seeing here is a direct line of sight where the light doesn't seem to be nothing of diffused. If anything, it might be spread out to 3 to 4 meters.
I don't see any.
For you to claim that the scattering I don't see how the scattering is helping you, to be honest. Like, yeah, scattering is probably taking place, but the light source that is being seen, it's not being diffused.
Okay. Let's just make sure that there is no picture that I have found in this document which shows a direct line of sight. What we see is the target for observation location. Are you seeing that picture? It's on the measurement 6. It's from 2:19 a.m. It's all that stuff. These temperature and humidity things. It's like 2 pages after all the data we've been working on. If you look at that light point, a direct line of sight laser point, it is so unfocused and scattered. It is clearly diverging upwards.
Sorry, Robert, is that the picture under technical data with a 3 by 3 meter surface?
So wait.
At the end of the document under technical data.
Is pretty much in the middle of the.
So this is the part that I'm
go
trying
to
to
the end of
see
the
how
document.
scattering or
data. 3 meter thing with a light shining on it. Light that's next to it.
So here's the thing I'm still confused about. Like this, let's just say it's scattering, right?
I misled you. Sorry about that.
So this scattering, the part that I don't understand is like now you're claiming that not only is it scattering, but it's going around the bulge, this 90-meter bulge that should be in between.
What I'm saying is
right.
The light.
Like, you have to think about it. It's like not only is it going to scatter, the light has to go around a bulge now that is 90 meters. That's what you have to believe if that's what you're claiming.
What happens
is the light is not only so the light is not only bending up again, but it has to come back down, right, for it to be observed. What kind of refraction is that?
It's called the magic refraction, Jose, where it just it diverges and yeah, exactly, magic.
That sounded like a lot of mental gymnastics just to make it work, Robert.
Well, can I explain, or are you just going to yell at me?
Oh, go ahead, please, man.
Is this the new standard globe argument where people complain about being yelled at because it's kind of boring?
I'm not complaining. I'm just saying, can I talk? Because I'm
not yelling. I'm sorry if my voice.
Yelled at you, dude.
I'm completely triggered.
Hold on a second.
I understand that.
Earlier we had a guy complaining about being yelled
at. You guys are dumb ass.
No, Robert, please, man, get to your point.
Can I just say this though? Yeah, we're not really into concern trolling.
Sorry, I don't associate with niggers.
Right. Cool. So yeah, just get on with the science. No one cares if you feel like you're being yelled at.
I'm not getting the option to actually answer any of the questions. I'm getting lots of questions thrown at me, and I'm just not getting the airtime to talk. That's all. I'm not pissed off with anime at all.
You understand our point, though.
Yeah, I completely see that you find that strange. So I'm trying to explain what's going on. You have this 90-meter bulge.
Yes, just crack on.
This 90-meter bulge, right? And then you shine a divergent light across it. Some of that light is going to hit the surface of the water, right?
We do not know that. If we are sufficient height above the water, we shall not hit it. And if the height of the starting height was roughly 3 meters above the surface of the water, and at 40 kilometers, the beam divergence, which we already know, which is 0.08 milliradians, right? You know, at that distance, 40 kilometers, we should just start to touch the water. Okay?
There was
so,
no atmosphere.
What I don't get, I'll give you the, okay, it refracted, it bounced, and it got absorbed, all that. How did it recollimate and hit the object?
It does not recollimate. That is the whole point. If you look at the photo, if you look at the target observation, it's not collimated at all. It is a huge smudge.
Smudge?
It is a huge smudge. Have you looked at the picture? It is nothing like a light beam.
Send me the picture. Send me, or just post
2 pages after. Wait, hold on. I'll just click it and just get it.
Yeah, just give me a snapshot. Just get it over with.
So
I really have to run.
Keep going back to between these two aspects here, refraction and scattering. Okay, now refraction. Can you give me evidence that light refracts down at night?
Sure.
Especially if you looked at the weather conditions for this type of measurement right here, they took the meteorological data and they showed that there was negligible refraction. Like the way they could test this out too is by hitting those points. If there was any type of refraction, there'd be a big. I'm not done. There'd be a big deviance from the 1 meter target that was 6 kilometers, 12 kilometers. That's why they did a horizontal pan and managed to see it in all 3 points. If the refraction was there that you're claiming, it would not be visible from all 3 points. It'd be different. So, like, really what you're doing is mental gymnastics right now. And I get it. Like, you don't want the FECORE to be a, like, you know, you need to find something wrong with it. But the problem is that it's not, it can't be explained with the globe. It really can't. Because now it's not just 1 meter, 41 kilometer meter mark. It's 3 points that are seeing the same observation with the horizontal pan. So now what type of refraction is it going to not happen in the 2 first points, but now you're claiming it's happening on the 41 kilometer mark, which I do agree. There'll probably be a little bit more refraction because it's a longer distance.
I'm saying scattering. Okay. Have you looked at the picture I sent you?
Yes, I have, sir.
Yeah.
Yes, I have.
You see that is not a color.
My question to you, that divergent beam that refracted and it got absorbed and all that, sure. Okay, how did it fly around the 90-meter bulge? Did it follow the curvature of the Earth because of the magnetic field or what? I would like to know your answer.
There's absolutely no magnetic field. There's nothing forcing it around the globe, obviously. But it means that every time it strikes the surface of the water, it's going to have a diffuse reflection. It's not going to be a mirror. It's going to be spread in all directions.
I am 100% with you.
What is it reflecting off of?
The light is going to be bounced off
the surface of the water.
It's bouncing off the front of the hump or the back of the hump.
Some of it's going to go back.
So the angle of incidence equals the angle of reflection, right? So if it hits the front of the hump, it's going to reflect into space. If it hits the other side of the hump, I don't know how that happens either because it just did a U-turn.
Impossible. It's impossible.
And how you're getting this idea.
You would never be able to hit your target.
Seem to think that when light strikes
Listen,
water,
obviously the beam is blurry because it's 25 miles. It's quite a long ways away. That's far, right? So of course it's going to be blurry and it's not going to be crystal clear. That's not feasible.
Can we give him 60 seconds to just respond? Because he has to leave.
Yes,
so I think we all understand that we want to keep him here, right? But he has a life, so let's just give his 2-minute closing or whatever, and then let's just let him go because we're gonna have to agree to disagree here, guys and gals.
We're never gonna convince each other, and I think actually it's kind of cool. Can I just say?
I want to know your math. I want to know your science behind this. It's not about you're gonna make me agree with you. It just show me how you can do that. Like it's gonna reflect off into space, right? Just show me how. It's gonna come back around. Okay. I assumed that the water is a mirror. I gave you that. Water is a mirror at point of tangency. No problem, bro. Now what?
All right, stop now. Let me talk. I need to leave, okay?
All you, sir.
The first thing I like to say is I feel like the FECORE measurements are actually really cool. I think it's important that it gets done. I'm not trying to fight you on this one, and we're never going to agree on what they show us, but I think it's important that you're actually doing actual science. So great for that. What I'm trying to say is that
science is an observation. Jesus.
Okay, just let him finish, please.
When light strikes
interrupt.
the surface of water, the surface of water, it is not like a mirror. You can't see a reflection of the sun in the ocean like that. You see a long, stretched out thing because that's how the reflection on water works. It throws light in all different kinds of directions. It does not work like a mirror. So when you have light touching the surface of the water, the light beams are going to go in all kinds of different directions because of the diffuse reflection that's going on. Some of that's going to follow the edge of the curve of the Earth. Some of it's going to go into space. We're only going to see the stuff that follows the curve.
How is it going to follow the curve, bro? That's what I'm saying. By me, like, assuming that I gave you water as a mirror, which is impossible, I'm helping you out. Like, now you have to explain to me, how is it going to follow the curve? I gave you a way out with the magnetic field, but show me your way out. How are you going to do this? How is the light following the curve, like you just said?
Well, can I say one thing? The refraction would have to be 100 times larger than standard refraction. 100 times. Okay, this would only work on an Earth that's a 65,000-mile radius. You understand that?
Not talking about refraction. Okay, so yet again, when light hits water, it gets scattered in all different kinds of directions. Some of it goes up, some of it goes way up, some of it goes horizontally.
Cool.
Great. So that means when you hit the surface of the water, some of that light is going to go horizontally.
Okay.
And the atmosphere, and then hit the water again. And a little tiny bit of it is going to go pretty far around the curve.
How is it going to go around the curve?
Skipping like a rock around the curve of the Earth. Skipping like a rock. The light's just going point, 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 and then going into the, is that what you're saying? I mean, I don't understand.
That a tiny little piece of it, yes.
It is. It is. Really? That's an interesting light, bro. That's very interesting light.
If you think I'm saying that the entire light is doing that, then you're not listening to what I'm saying. I'm saying that.
Well, how much of it?
I heard what you said. You said a tiny bit of the light would skip like a stone across 25 miles. I think you're going to have to demonstrate that.
And would that be enough to illuminate the object with that same luminous intensity? Now we're speaking science, dude. Right? Now we're on the same playing field. With this scattered skipping stone of yours, would it illuminate the object with that same intensity? Now you're gonna have to do some math.
I don't know what the intensity is, so I can do that. But we can predict how much of the intensity that would be.
Let's go. Well, let's go. Whatever software you want to predict it with, I'll fire it up. How you want to do this?
But I'm gonna have to go, as you know. As I said, I'm not trying to.
I know, man.
We can do it, but I have no idea what the target is. That in the document? How much intensity we get back? We know how much of the. Do we know how much of the laser when we get back?
If we start out, if we know the laser intensity that we're starting out with, we can work some stuff out, man.
No, I mean,
we need to get the sensor size, then the beam diameter, and then you take that cross section of the divergence at that point, and then take the, that little area that the sensor would be. Well, actually, the lens. Then you could figure out how many photons would fall onto the sensor. I mean, Jesus, do we really need to be that particular?
I get that part completely, but do we have a measurement? Do they have measured how many photons they actually got? Because that's what we need to test my hypothesis, because that's what that is. What happened? If we don't have that data, we can't test it.
Your skipping stone hypothesis isn't real. Just, you know what I'm saying? It is not real. We gave you that for free, but it is not real. It's not observed.
You can deny it if you want. That's how how non-specular highlights work. That's how diffuse refraction works. That is how light bounces off something which isn't shiny.
Around the curvature, but if you have mass in between, you're gonna reflect behind the mass somehow. This bulge, you got this bulge of water in between you and the target. Now this is gonna scatter around. So how much? And what is the losses of scattering to distance?
I have no idea.
To the inverse square law or what?
Inverse square. It's going to be pretty intense. That's why we need to know how much.
Right. You're not going to get any light, man. It's just like, dude.
90 meters is like a 30-story building, right?
It's a big curvature. I agree with you.
It's just like a 30-story hill, man, like that you have to get around. You're saying you can be on the other side of the hill, and there's a light source on the other side, of this 90-meter hill, and somehow you can see that light. I don't know that that's ever been observed ever in the history of mankind.
Well, have been like some kilowatts, man, of power to illuminate something.
I mean,
at that
and isn't
distance for a
water
bulb.
absorptive of blue light?
Hold on, I'm just checking if this distance is even plausible. Where's the targets here? Anyway, yeah, as I say, I think it's a fun experiment. I think it's fun to look at. I would like to have known the target intensity. That would have been useful, but we don't have that. But it's cool. So with that, I'm going to have to run. I've been here for way longer than I thought I would be.
Thanks for stopping by, Robert.
Thanks for
Appreciate
coming
your
here.
time, man.
Thanks for coming here and giving it a shot.
Come back anytime you want to get schooled, bro.
I'll get the WMAP data for your next time you're on here, bro. I got you. Don't worry.
Yeah.
All right, have a good day. All right,
Yourself,
you too, bro.
Now,
Peace out, Rob.
Peace.